There is a telescope floating in space right now, about 1 million miles from Earth, wrapped in a sun shield the size of a tennis court, cooled to temperatures colder than anything that exists naturally in our solar system. And what it has been seeing, what it has been sending back to us, is quietly dismantling some of the most fundamental ideas we have ever had about how the universe works. I want to be careful with that word, dismantling, because in science, that word gets thrown around a lot. Every few months, someone somewhere announces a discovery that will supposedly change everything. Most of the time it does not. Most of the time it is a refinement, an adjustment, a small correction to a model that continues to work pretty well. But every now and then, something comes along that is genuinely different. Something that does not just tweak the model, something that makes serious, credentialed scientists stop what they are doing and say, quietly but honestly, we might have gotten something wrong. Something big. What the James Webb Space Telescope has been finding in the early universe is that kind of something. To understand why what Webb is seeing is so extraordinary, you need to understand what we expected to see. And to understand that, you need to start from the beginning. The actual beginning, as best as we understand it. About 13.8 billion years ago, the universe began. This is the event we call the Big Bang, though that name is a little misleading because it was not really an explosion in the way we normally picture one. It was not an explosion that happened inside space. It was the beginning of space itself, the beginning of time itself, the initial moment when everything that exists, all the matter, all the energy, all the fundamental forces, erupted into being from a state of almost incomprehensible density and temperature and began expanding outward. In the first few minutes after the Big Bang, the universe was an extraordinarily hot, dense soup of fundamental particles. No atoms, no molecules, certainly no stars or galaxies. Just energy and elementary particles crashing into each other at enormous speeds in a universe that was rapidly cooling and expanding. After about 380,000 years, the universe cooled enough for the first atoms to form, mostly hydrogen and helium, the lightest elements, and the light that was released at that moment is something we can still detect today as the cosmic microwave background radiation, a faint afterglow of the Big Bang that fills the entire sky. But after that first light, the universe entered what astronomers call the cosmic dark ages. There were no stars yet, there were no galaxies, there was just hydrogen and helium gas slowly drifting through an expanding dark featureless universe. Gradually, over time, slight variations in the density of that gas began to matter. Places where the gas was just a little bit denser than average had slightly stronger gravity. They pulled in more gas from their surroundings. Over millions of years, these dense regions grew denser. The gas began to compress and heat, and eventually, the first stars ignited. Then those stars gathered into the first galaxies, and the universe, after hundreds of millions of years of darkness, began to light up. That is the broad outline of the story, as our best theoretical models have described it. And it is a story built on a very specific idea about how structure forms in the universe. The idea is that galaxies did not just appear suddenly, they grew gradually, seeded by something called dark matter. Dark matter is one of the great mysteries of modern physics. We cannot see it. It does not interact with light in any way we can directly detect, but we know it exists because of its gravitational effects. The way galaxies rotate, the way galaxy clusters bend light, the way the large-scale structure of the universe is distributed, all of it points to the existence of enormous quantities of matter that we simply cannot see. About 27% of the total energy content of the universe appears to be dark matter, compared to the roughly 5% that is ordinary visible matter. The stars, the planets, the gas, the dust, everything we can actually observe is only a small fraction of what is actually out there. According to our standard model of cosmology, dark matter was the scaffolding on which ordinary matter was assembled. In the early universe, dark matter began clumping together first, forming what cosmologists call dark matter halos. These halos then gravitationally attracted ordinary matter, pulling hydrogen and helium gas into their cores, eventually allowing that gas to cool and collapse further and form the first stars and galaxies. The key point is that this process takes time. Dark matter halos need time to grow large enough to seed significant galaxy formation. Under the standard model, the very early universe, within the first few 100 million years after the Big Bang, should contain only small, primitive, relatively simple galaxies in the early stages of formation. The big, well-developed, massive galaxies we see all around us today, those took billions of years to build up. That is what the theory predicts. That is what we have believed for decades. And it is the prediction against which we now have to measure what the James Webb Space Telescope is actually finding. Here is the thing about observing the early universe. It is not easy. In fact, for most of human history, it was simply impossible. When astronomers look at distant objects, they are not seeing those objects as they are today. They are seeing them as they were in the past, because light travels at a finite speed. The light from an object 1 billion light-years away has been traveling for 1 billion years to reach us. We are seeing that object as it was 1 billion years ago. The farther away an object is, the further back in time we are looking. So to see the early universe, to see the first galaxies, we need to look at objects that are extraordinarily far away. But there is a complication. As the universe expands, the light from distant objects gets stretched. The wavelength of the light increases, it shifts toward the red end of the spectrum, and then beyond, into the infrared. This effect is called redshift, and the amount of redshift in an object's light tells us directly how far away it is and how early in cosmic history we are seeing it. The higher the redshift number, the more distant the object, and the earlier the era of the universe we are observing. The problem is that the most distant, highest redshift objects emit their light almost entirely in the infrared, and infrared light is invisible to optical telescopes. The Hubble Space Telescope, which has been one of our greatest tools for studying the distant universe, was designed primarily to observe visible and near-infrared light. It could push into the high redshift universe a little, but only a little. The farthest galaxy Hubble could reliably study had a redshift of about 11, meaning we were seeing it as it appeared about 400 million years after the Big Bang, and even finding that galaxy was considered remarkable. Astronomers believed that the universe at redshifts above 11 was largely empty of the kind of galaxies Hubble could see. The standard model suggested it should be. The James Webb Space Telescope was designed to change this. Webb was built specifically to observe the infrared universe with unprecedented sensitivity and resolution. It can see things that were simply invisible to every instrument that came before it. Objects at redshifts of 12, 13, 15, and potentially beyond. Objects that formed within the first few 100 million years after the Big Bang. Objects that no human instrument had ever been able to study in detail. When Webb turned toward the deep sky and began its observations, the expectation was that it would find the early universe looking more or less the way our models predicted. A few small, young, primitive galaxies scattered sparsely across a dark, mostly empty cosmic canvas. The scaffolding of dark matter halos just beginning to accumulate. The universe in its infancy, sparse and simple. What it actually found was something very different. Instead of a sparse, nearly empty early universe, Webb revealed dozens of galaxies at extremely high redshifts. Galaxies that had formed in the first few 100 million years after the Big Bang, far more of them than expected, and many of them far more developed and massive than they had any right to be at that age. One after another, as astronomers analyzed the data coming back from Webb, the discoveries began to pile up in ways that strained the standard model. A galaxy called Galaxies Z13, for example, was found with a redshift of 13.2, meaning we are seeing it as it appeared only about 300 million years after the Big Bang. At that age, under the standard model, a galaxy should be a modest, sparse, early-stage structure. Instead, Galaxies Z13 appears to be a reasonably well-formed galaxy. Finding something like this so early was already surprising, but it was just the beginning. Webb found another galaxy appearing just 390 million years after the Big Bang, then others even earlier. With each new observation cycle, the timeline kept getting pushed back. Galaxies appearing earlier and earlier, more fully formed, more numerous, more massive than the standard model had predicted would be possible. And then the Webb data produced something that elevated the puzzle to a completely different level. While searching through Webb's deep field images, a team of astronomers found something they initially struggled to explain, an extremely red object, far redder than anything they expected to find in that region of the sky. Red objects are, as we have discussed, typically distant objects because the expansion of the universe stretches their light toward longer, redder wavelengths, but this object was unusually, almost strikingly red. More red than the redshift from its distance alone would explain. The astronomers began working through the possibilities. Could it be something relatively nearby? Perhaps a dusty object within our own galaxy, or not far beyond it? Dust can make objects appear much redder than they otherwise would, because dust absorbs shorter wavelength blue light while letting longer wavelength red light through more easily. But this explanation did not hold up. The object appeared extended in the images, not point-like as a nearby stellar object would appear, and astronomers tracked it for over a year without any change in position. A nearby object would show some detectable motion against the background of distant galaxies. This one showed none. It was not nearby, it was very far away. So the team worked through three possible interpretations. The first was that it might be a dusty dwarf galaxy located somewhere around 4 to 5 billion light-years away. This would make it far from ordinary in some respects, but not catastrophically challenging to existing models. But when they looked more carefully at the data, this explanation started to seem increasingly unlikely. The numbers simply did not add up in the way they would need to for this interpretation to work. The second possibility was that it could be a more distant, dust-shrouded galaxy that existed about 1 to 2 billion years after the Big Bang. Again, this would have been an interesting finding, but not an earth-shaking one. But again, when the evidence was examined in detail, this explanation also failed to account for everything they were seeing. And then there was the third possibility, the one that made the scientific community genuinely sit up and pay attention. The researchers proposed that this mysterious object might belong to the same class as a group of objects that Webb had already been puzzling over. A group informally called the Little Red Dots. These are compact, intensely red galaxies that Webb has been finding at very high redshifts, galaxies that appear far more massive, far more luminous, and far more developed than our models say they should be at that point in cosmic history. They are too bright, too big, too well-formed for a universe that had barely had time to get started. And the analysis of the new mysterious object suggested it might be even more extreme than the little red dots already known. The estimated redshift for this object was placed at around 15. A redshift of 15 would mean we are seeing this object as it appeared just 100 million years after the Big Bang. 100 million years. In the context of a 13.8 billion-year-old universe, that is nothing. That is less than 1% of cosmic history. Under the Standard Model, the universe at that age should be in the very earliest stages of galaxy formation. There should be almost nothing there yet, at least nothing that looks like what this object appears to be. And yet, if the measurements hold up, something was there, something massive enough to produce the light we are seeing. Something developed enough to have the properties this object seems to have. If confirmed, this would be the most distant galaxy ever observed. And it would represent a serious, direct challenge to our current models of how the universe evolved. Now it is important to say something here that sometimes gets lost in the excitement of these announcements. This is not yet confirmed. The redshift of 15 is an estimate, spectroscopic confirmation, where astronomers carefully analyze the detailed spectrum of the object's light to get a precise redshift measurement, has not yet been completed for this object. It is possible that when the full analysis is done, the object will turn out to be at a lower redshift, and the situation, while still interesting, will be less dramatically extreme. Science works this way. Candidates emerge, they get scrutinized, and sometimes the initial interpretation changes. But here is the thing. Even setting aside this one mysterious object, the overall pattern from Webb's observations of the early universe is already established and already troubling for the Standard Model. It is not just one galaxy that is too massive, too developed, too early, it is dozens of them. The pattern is consistent enough that serious, mainstream astronomers are openly discussing the possibility that something in our fundamental models of galaxy formation needs to be revised. Claudia de Ram, Associate Professor of Astronomy at the International Center for Radio Astronomy Research, stated directly that the presence of these extremely massive early galaxies presents a serious challenge to our current model of cosmology. The dark matter scaffolding that our theories require to have been in place to seed early galaxy formation simply should not have existed in sufficient quantities at those very early times. And yet the galaxies are there. One possibility that researchers are now actively discussing is that some galaxies may have formed through mechanisms that did not rely on the expected dark matter halos in the way the Standard Model Predicts. If that is true, it would not just require tweaking a parameter somewhere in our cosmological models, it would challenge one of the central pillars of modern cosmology. Dark matter is not just a side detail in our picture of the universe, it is foundational. The role dark matter plays in seeding structure formation is woven throughout our understanding of how everything from galaxies to galaxy clusters to the large-scale web of cosmic filaments came to exist. If early galaxies formed without the dark matter scaffolding we thought was necessary, then something deep in that picture needs to change. Some researchers are looking at this and asking an even more fundamental question. What if the issue is not just with galaxy formation models? What if it points to something deeper, something about the nature of dark matter itself, or the timeline of the early universe, or even aspects of the Big Bang model that we have taken for granted? These are the kinds of questions that start to lead scientists into genuinely uncharted territory. Some of the proposed explanations remain firmly within conventional physics, requiring adjustments to parameters within the existing framework. Others push further, invoking new physics, modified theories of gravity, different models of how dark matter behaves in the early universe, or new ideas about the processes that drove the first bursts of star formation. And then there are ideas that venture beyond our current physical framework entirely. Some researchers have proposed models in which our universe is not the only one, in which we exist within an enormous multiverse of parallel universes, each with potentially different physical laws. Others have proposed cyclical models in which the universe does not have a single beginning, but instead goes through endless cycles of expansion, contraction, and rebirth. These ideas are highly speculative. Most of them are not yet testable in any direct way, but the fact that credentialed physicists are taking them seriously enough to publish papers about them tells you something about the depth of the challenge that Webb's observations are posing. Perhaps the most intriguing theoretical response has come from Nobel Prize-winning physicist Roger Penrose. His framework, which he calls conformal cyclic cosmology, proposes something genuinely strange and fascinating. It suggests that our universe may have been preceded by an earlier cosmic era, that the Big Bang was not an absolute beginning, but rather a transition point, a kind of boundary between one cosmic age and the next. Under Penrose's model, what we call the Big Bang was actually the end of a previous universe and the beginning of ours, connected through a geometric transformation that preserves certain physical information. It is a deeply unconventional idea. Most physicists are skeptical of it. But it is the kind of idea that Webb's observations are creating room for, because when the standard picture starts to develop serious cracks, unconventional ideas start to deserve a more serious hearing. What all of these ideas share is a recognition that the early universe is not behaving the way we thought it would. Something formed faster than it should have. Something became more massive, more complex, more structured than our models allow in the time available, and the James Webb Space Telescope is the instrument that is forcing us to confront this. Not by suggesting failures in our observations. The data from Webb is extraordinarily high quality, but by showing us, with beautiful clarity, a universe in its infancy that looks more developed than the standard model can comfortably explain. There is a broader perspective here that I think deserves to be said plainly. We have been building our standard model of cosmology for decades. It has been enormously successful. It explains the cosmic microwave background radiation. It accounts for the large-scale structure of the universe, the distribution of galaxies across cosmic space. It explains the abundances of the lightest elements formed in the Big Bang. It has passed test after test across many different areas of observation. It is not a flimsy theory. It is a robust, carefully constructed framework that has earned its place as our best description of the universe. But science is not about protecting theories. It is about following the evidence. And right now, the evidence coming back from the James Webb Space Telescope is telling us that something in our best framework may need to change. Not be thrown out entirely. Probably not. Most likely, what is needed is a significant extension or revision of certain parts of the model, perhaps our understanding of how the first galaxies formed, perhaps our picture of how dark matter behaves in the early universe, perhaps something about the physics of star formation in extreme early conditions. But it is also possible, and this cannot be ruled out, that what Webb is finding points to something deeper. Something that requires a more fundamental revision of how we understand the universe's origins and early history, What I find most remarkable about all of this is not the specific discoveries, as stunning as they are. What I find most remarkable is the process. Here is a telescope built by human beings, launched into space, pointed toward the oldest light in the universe, and sending back images that challenge ideas that thousands of scientists have spent careers developing and testing. And the response of the scientific community is not defensiveness, it is not denial, it is exactly what science is supposed to look like at its best. Careful scrutiny of the data, honest acknowledgement that something unexpected is happening, active search for explanations, willingness to consider that cherished ideas may need to change. The universe does not owe us simple answers. It does not owe us a cosmos that behaves the way our models predict. And what the James Webb Space Telescope is teaching us, above all else, is that the universe in its earliest moments was wilder, richer, and stranger than we had imagined. Every image that comes back from Webb is a message from the deep past. Light that left its source hundreds of millions, or even more than 1 billion years before Earth formed, finally completing its journey and landing on a detector in a telescope built by the inhabitants of a small rocky planet that did not even exist when the light began traveling. And what that ancient light is telling us is that the early universe was alive with structure and complexity far sooner than we thought possible. We are in the early stages of understanding what this means. There will be more observations, more data, more analysis. The mysterious extremely red object may turn out to have a perfectly orthodox explanation. Or it may turn out to be exactly what it currently appears to be, the oldest, most distant galaxy ever seen, a galaxy that should not exist when and how it seems to, a galaxy that demands we rethink some of our deepest assumptions about the cosmos. Either way, we are living through a genuinely remarkable era in the history of astronomy. The James Webb Space Telescope is not just finding new objects, it is asking new questions. And in doing so, it is doing the most important thing any scientific instrument can do. It is reminding us how much we still do not know, how much is still out there waiting to be understood, how the universe, even after decades of extraordinary scientific progress, can still surprise us, challenge us, and pull us forward into deeper and more beautiful mysteries. The early universe is not what we thought it was, and figuring out what it actually was and what that means for everything we thought we understood is going to be one of the defining scientific endeavors of the next generation. We are just getting started.